Okay, so in this video, we're going to continue our discussion of orbitals, exactly how electrons go into them in the end, kind of what this affects, and how we can identify core and valence electrons and all of this good stuff. So, why does all this information about orbitals matter anyways? So I was being a bit vague about orbitals last time. We were trying to just nail down these models and understand what the heck I was talking about, that electrons aren't exactly real anyways. I just want to remind you again that electrons are both a particle and a wave of probabilities where that particle exists. So they exist as this wave of all the options of locations of where they could be until they are observed and forced to choose one exact location. And remember that orbitals tell us about these probable locations of the electrons in the electron cloud. So we never know the exact locations of electrons around an atom. So we use orbitals to tell us how likely it might be to run across a certain electron in a certain space, kind of deal. Different orbitals have different energies of sort of generally increasing from the center of the atom outwards. And when they jump orbitals, electrons do. That's what causes our emission spectrum still. And we can use the probabilities given by these orbitals to fill in the most likely locations of our electrons around an atom. So based upon the locations of these electrons and how easily atoms can therefore form bonds and how many bonds they can form, of course, affects the chemistry that everything is involved in. Okay, so we're talking about orbitals. We gotta start talking about how to name the orbitals, how to talk about them. Been kind of vague about it. It's time. So orbitals are denoted by both a number and a letter, okay? So one tells us more about the energy and one tells us a lot about the shape. So when we're talking about the number, this is called a principal quantum number. So this denotes the general energy level of the orbital. So we usually see this denoted as n equals 1, n equals 2, n equals 3, and n equals 4. So the energy levels are basically kind of like fixed distances from the nucleus. So rather than being, again, that individual ring, this is representing kind of a spatial distance, 3D space around the nucleus. But it's not like exactly saying like there's a ring, because there's all these other informations about the shapes of the orbitals and the likelihood of electrons to lie in those as well. However, generally, as you increase distance from the nucleus, you're increasing the energy level, so the principal quantum number increases to represent that. So an n equals 1 energy level is going to be lower than an n equals 2, is going to be lower than an n equals 3, and n equals 4. And as we start to get up in energy levels, they become closer and closer together. And because they become closer and closer together, we'll see that this has some funky effects on the way we fill our orbitals, but that's just a huge preview. So again, the principal quantum number denotes the general energy level of the orbital, kind of the general how far it is from the nucleus, and things that have high energies, have high principal quantum numbers, and are further from the nucleus. So you can have multiple orbitals of different shapes, like that S shape we saw last time, the P shape, and that D shape. So we could have orbitals of different shapes all have the same principal quantum number. And so we would call this a principal shell. So a principal shell is all the orbitals with the same principal quantum number. The book uses this term more than I will. You probably won't hear it out of me again unless I'm trying to explain something and I have no other word. But again, this is all of the shapes, all of the letters that have the same number are a principal quantum shell. Or principal shell. Sorry. Okay, so we talked about the numbers. Well, what about the letters? Well, as in like the first half of the first video, we know that we can use letters to denote the shape of the orbital. So I'm in the way here, but remember the s orbital is that circular sphere shape. The p orbitals are made up of 3 dumbbell shapes, and the d orbitals are made up of 4 four-leaf clovers and a donut with a dumbbell. Kind of a deal. So this is an s orbital, a p orbital, and a d orbital on your screen. So We use these, or we have these different shapes, and we can kind of call these subshells. So if the principal quantum number, all the same principal quantum number is a principal shell, these are the subshells. Again, you probably won't hear me use this term quite so much, but the book uses it, so it's out there. So the shapes also have a generally increasing order of energy, right? So things that are close to the nucleus are low in energy, and things that are further from the nucleus are higher in energy in general. We talked about that, right? So when we're looking at an s orbital, it's this sphere around the nucleus. So really, it's close in by the nucleus. They tend to be lower in energy levels. P's tend to be higher in energy levels. We can see that the electron density, where it's the highest concentration of where an electron might be, is a little bit further away from that nucleus. And they're in these three different positions kind of all the way around, excluding that center. So that's a little bit higher in energy. They tend to just be a little bit further away than the electrons in an s orbital. And then in d orbitals, you see it spreads them even further out. It's less likely that these are going to be, or that the electron's going to be very close to the center of that atom. So as you increase from S to P to D, you generally increase in energy, just like when you increase the principal quantum number. However, the principal quantum number tells you more information about the energy than this does. And the thing is that these, we're not like kind of nailing down a specific amount of energy, but because they also increase in energy, and because we have principal quantum numbers increasing in energy as well, we'll see that there's a little bit of a funky thing that happens in just a second here. So just keep in mind that these increase in energy as well. So again, just to give it a little bit more of an analogy, I'm going to use 2 or 3 today. So this is just the first for just this scenario that I want to discuss. It's almost like the principal quantum number is sort of like the country. So I could tell you I'm in the United States, but I could be in all 50 of the states, any of the outlying territories, whatever you want to call them. So I'm in the United States. It doesn't really tell you a whole lot, but it at least tells you what country I'm in. The letter is like the state of the union the electron lives in. So it's a more specific piece of location information kind of hidden in there. So if I tell you I'm in Illinois, you have a higher chance of finding me than if I tell you I'm in the United States. So that's kind of the idea here. It's like we've got a state, and then that energy level, that n equals 1, n equals 2, n equals 3, n equals 4, so on and so forth, that's going to be more like a general piece of information. And again, as I mentioned before, these orbital shapes kind of come in groups. So S is only made up of 1 orbital, but P is always made up of 3 orbitals, and D is always made up of 5 orbitals. So these are almost like kind of the towns in the state. We can narrow down our state into just a little bit more piece of specific information even. It's not just a broad idea. So again, anytime we see a p orbital, we're talking about 3 different sets, or like one set of 3 different options for locations. And when we're talking about a d orbital, we're talking about 5 different options, all combined to one to make one d orbital. So here it is, the slight catch I mentioned before. So again, while orbital energies kind of, you got the principal quantum number increasing in energy, and while the orbital energies generally increase as you go up in shape from S to P to D to F to G to H. I didn't mention those, but they technically exist. We won't talk about them in this class. But in reality, it doesn't just exactly work where you go 1s, 2s, 2p, 3s, 3p, 4s, so on and so forth. It gets a little weird. So actually, when things increase in energy, we go from 1s up to 2s, up to 2p, up to 3s, up to 3p, up to 4s. Makes sense so far. But wait, what's this guy over here? 3D is kind of out of order. Basically, because the D shape is such a high energy, 3D ends up being a higher energy than 4S is. So it's higher in energy. It kind of breaks some of the ideas we have about distance and these shapes and stuff like that. But when we actually look at it in real life, this is how everything is affected. So it kind of takes things out of order just a tiny bit. Okay, so now we know all about orbitals. We've talked about what they are, the nature of all of this. Now how do we actually put the electrons in them? They're probability maps. How do I figure this out? So here's my second analogy. So the first one kind of talks about the difference between principal quantum numbers and the letters representing the shapes, those subshells. Now we're going to talk about orbitals as locations for electrons, okay? So let's think about orbitals now as all the rooms in a hotel. The hotel is the electron cloud of the atom, and the orbitals are like all the hotels in a hotel room, and electrons are like the people going into rooms. Let's say it's a honeymooners weekend, right? So we've got pairs of people that need to go into rooms potentially, and they might be arriving at different times, let's think. So when you're booking a hotel, you don't just put any kind of person in any room, right? You know, everybody wants to stay with their spouse and to have the people around them that they love, right? They don't want to stay with some random person they've never met before. You don't just throw random people into random rooms at random times. There's order to how you put people in hotel rooms. And you do not cram all 100 guests you have staying in the hotel at night into one 2-bed room. You don't do it. You have to spread them out throughout the rooms in the way that makes sense, that gives them the best option for what they need. So let's do it. Let's put our electrons in their rooms, tuck them into bed, and say goodnight. So orbitals are like the likely space for a certain number of electrons to exist. So we're going to use some guidelines to place our electrons in there. So how do we do this? We actually call a visual display of the location of the electrons in their orbitals an orbital diagram. So when I'm looking at the things that are pictured on your screen here, all these weird looking boxes, these are what we call orbital diagrams. So each arrow represents an electron. So lithium has 3 electrons. So this is 1 electron, 2 electrons, 3 electrons. Kind of see they got that weird half-looking arrow. So they have that weird half-looking arrow. It's showing us something. We don't know quite what it is yet. So they're these weird half-looking arrows. And each box is an orbital. Okay, putting electrons in orbitals, I'm going to put electrons in a box. So remembering that S is always just 1 orbital, but P is made up of 3. So I'm going to use 3 boxes for P, and I'll use 5 boxes for D, because again, a P is always made up of 3, a D is always made up of 5, but S is always just 1 box. We tend to write the number and letter of the orbital down below. So the number and the letter, so this would be the name of the orbital. I said write letter and name, but letter and number, that is the name of the orbital. So 1s, 2s, 2p. And we group the orbitals together with the same number and same letter. So we're scooching all the p's together, the 2p group. We're scooching them together as a group is what I'm saying. We're not going to like space out all of the 2p orbitals from each other. Each orbital holds 2 electrons at maximum. We consider one to be spin up and one to be spin down. So that's what that half arrow means. This one's pointing up and this one's pointing down. It's a half arrow because now it's a part of a pair. So spin up and spin down is kind of a weird concept. As we move into this quantum mechanical model, things kind of become very abstract. So spin up and spin down has nothing to do with spinning. It is just a word we use to describe a characteristic that basically says these two electrons have decided to be a pair together and they're willing to hang out with each other as long as one takes one version of the characteristic and the other takes the other version of the characteristic. So we call that characteristic spin, and we say that one electron is spin up and one electron is spin down in a pair. Okay? It has nothing to do with up and down. It has nothing to do with spinning anything. It's just like we decided one day that this hand was left and this hand was right. There's no reason for us to have chosen one word over the other to have meant one. We chose arbitrary words to describe something so we could talk about the difference between two things. That's what we've done here. We have chosen spin up and spin down. And now this is why electrons are able to form those pairs that we saw in our Lewis diagrams, is because even though they repel each other, they kind of make this agreement, all right, you're spin up, I'm spin down, so we can hang out. I'm cool. As long as you're spin up and you stay in your lane and I'm spin down and I stay in my lane, we can hang. Otherwise, no go. Not happening. No. So, each orbital holds two electrons at maximum, one spin up, one spin down. We fill orbitals from the lowest energy to the highest energy. So in this case, we see here we have 1s, goes to 2s, goes to 2p. Makes sense. 1 is the lowest principal quantum number. 1s would be lower than 2s, and s is a lower energy than p. Makes sense. So we're filling our orbitals this way. We can see as we increase our number of electrons, we're filling our orbitals from 1s up to filling up the 2p orbital. And when we do this, we put one electron per orbital until we're forced to pair them up. Kind of like those Lewis structures when we were drawing them. That's again what's happening here, is it's because these electrons stay apart from each other in their orbital, they don't pair up until they're forced to. So that's what we were seeing happening without knowing it in the background. So it's kind of explaining some of the stuff we saw last chapter. Kind of cool. And so I just want to remind you very quickly here where these electron numbers come from. How do I know how many electrons something has? Well, remember, in a neutral atom that doesn't have a charge, the total number of electrons is equal to the total number of protons, and the total number of protons is given to us as the atomic number. So that atomic number is given to us, and that's also in our case here going to be our number of electrons, because it's the same as the number of protons that the atomic number represents. So, remember, as I said before, that we kind of have that weirdness in the energy levels, and we have to make sure we fill everything from the lowest energy level up to the highest energy level, okay? So we're filling from the lowest energy level up to the highest energy level. And we know that there's kind of these weird tricks where 4s is technically lower in energy than 3d is. So how can I remember this? How can I figure this out? How can I remember how electrons fill orbitals? Well, here's our periodic table. Now's coming in our periodic table explanation. So when we're filling these orbitals, we're filling them from 1s to 2s to 2p to 3s to 3p to 4s, all the way back to 3d to 4p to 5s to 4d to 5p to 6s, so on and so forth. That's kind of a funny, weird looking diagram though. How can I remember this? Again, our periodic table's back. It has all the information you could ever need. I do have one that has all the information you could ever need. However, this one's giving us a little bit more of a highlight about our orbitals and how our electrons fill our orbitals. So let me show you this. Anything in blue is considered a part of an s orbital. Anything in pink is considered a part of a p orbital. Anything in orange in the center here, the transition metals, that's the d orbitals. And down here at the bottom in green, we're not going to talk much about this, but these are the f orbitals. Again, we're not going to talk much about them in this class. This is the only time you're going to hear it. And so we might talk about this as the s block. So these are s block elements where their outermost electrons are in the s block. We'll talk about what that means later. In the p block, again, the p block is all of these elements that have electrons in the outer p, or that all of the outer electrons lie in the p orbital. Again, the d block here representing the same thing, and the f block down here representing the lanthanides and the actinides. So you might hear me say, oh, that's an s block element, that's a p block element, so on and so forth. And so, let me say this. Hydrogen and helium, their 2 electrons represent the 1s orbital. Lithium and beryllium, theirs are the 2s. These are the 2p. This is the 3s. This is the 3p. Okay? Row number 1 has the 1s. It only has s elements. Row number 2 has the p block too. So it has these 2p and the 2s and the 2p over here. So this is the 2s. I misspoke there. The 2s and the 2p. So when I look at the periodic table, I'm always in my head going 1s, 2s, 2p, 3s, 3p. Okay? So that row, for the most part, corresponds to the N number, that energy level number. So that energy level number is most of the time what you see here on the left-hand side of the periodic table. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. All right, it's weird. It feels wrong. Icky. Okay, so when we get to the D block, the first row in the D block is the 3D. So we go 1, 2, 3, 4, 5, 6, 7. That works perfectly fine for the S and the P. But when we get to the D, it actually starts at 3, not at 4. So this is the 3D block, okay? So that's kind of how you can remember how to fill your orbitals on the periodic table. My lowest in energy is 1s, then I would go 2s, then I would go 2p, then I would go 3s, then I would go 3p, then I would go 4s, then I would go 3d, then I would go 4p, then I would go 5s, then I would go 4d, then I would go 5p, okay? So at the very most, I will give you xenon. In this class, we're not going to go beyond xenon, and I will only be asking you to write the orbital diagrams and electron configurations of things in the S block and things in the P block. Things can get very bizarre in the transition metals in that D block, so we're going to leave them alone in this class. We're only going to talk about the S block and the P block up to xenon. So we're taking the first 5 rows and we're going to talk about the S block and the P block, not the D block. So you're not responsible for figuring things out with the F block, and you're not responsible for worrying about exactly how to write the electron configuration and write the orbital diagram for the D block. However, it will get incorporated into those drawings and the way you write those things out for things that are lower on the periodic table in like the 5s, 5p, 4p kind of space. So just keep that in mind. So how do I actually write these dang things called orbital diagrams, Emily? Well, here's just kind of a general list of steps. So first and foremost, you got to determine how many electrons you have. Remember, neutral atoms, so this is going to be the atomic number you see on the periodic table. Once you've done that, you need to determine the number and type of orbitals that you have. So use the location on the periodic table to tell you. So if I go back here and I want to know what's like kind of the maximum or biggest orbital or furthest one out or whatever the heck you want to call it, the like end thing I have to write down orbital for something like, let's say, chlorine, it's in the p block, so it's going to be a p orbital and it's going to be the 3p orbital. If I'm looking at arsenic here, that means that it's going to be the 4p orbital, including the 3d orbital, for example. So once I figure out how many electrons I have, I figure out where the kind of last electron would be in an orbital. So if it lies in the p block, and then what row it lies in. If it lies in the s block, what row it lies in. I want to know that. So I want to know like 4p, 4s, that kind of information. So first and foremost, number of electrons. Second and foremost, figure out kind of what that last orbital, that's the word I'm looking for. Figure out what that last orbital's gonna be. And then we're gonna draw out all the boxes. So you're gonna put 1 box for every s orbital, 3 boxes for every p orbital, and 5 boxes for every d orbital. And we're going to make sure you label them with their letter and their number below them, okay? You group all 3 boxes for a p orbital together. You smush all 3 boxes for a d, or all 5 boxes for a d orbital together. And then we write them in order of increasing energy. So that's going to be our 1s, our 2s, our 2p, our 3s, our 3p, our 4s, then our 3d, then our 4p, kind of a deal. So we're making sure we're kind of following that order that we would trace across the periodic table. Once we have this all drawn out, we've given us a base to write our things down in. You fill out the orbitals from lowest energy to highest energy. You're going to put 1 orbital, 1 electron per orbital, unless you have to pair them up. And you can put 2 maximum per orbital. So 2 maximum per orbital, and you only pair them if you have to. So when filling p and d orbitals, you fill each individual box of the 1 of 3 or 1 of 5 with 1 electron per box until you absolutely have to start pairing them up, and you have got to make sure you're writing them spin up and spin down. So if I had a hint for some of the things that I see wrong most of the time on orbital diagrams, it would be that you put the orbitals in the wrong order. So maybe you put 3d before you put 4s or something like that. So you got to make sure the orbitals are increasing energy order. And then maybe you start to pair up all the electrons rather than putting them individually. So you can't pair them up. Just like on the Lewis structure, you had to keep them separate from each other. So here again, you have to pair the electrons together. And the other mistake that I see, and this is absolutely critically important, I know it feels so arbitrary, but it's so important, it has to be written spin up and spin down. So if you mean spin up, write spin up. If you mean spin down, write spin down. Make sure you're drawing those half arrows up and down to represent spin up and spin down. You cannot put 2 spin up electrons in 1 orbital or it's wrong. So let's get to drawing. Let's get to doing it. Let's actually draw some orbital diagrams. So the first orbital diagram here we're going to draw is the orbital diagram for beryllium. So this is beryllium. This is Be. So when you're drawing these diagrams, you can either choose to use boxes like I have shown before, or you could draw blanks equivalently, something like this. So this could be the 1s, this could be the 2s, this could be the 2p. As long as you're able to group those blanks together in a way that makes sense, those lines in a way that makes sense, so that I know that these 3 together make up the p orbital. I don't care how you do it, but I prefer the boxes, so I'm going to continue to draw boxes throughout this presentation. So let's get rid of this and keep on with my boxes. So first things first, I'm a realist. No, I'm not Iggy Azalea, but first things first, I have got to figure out where beryllium is located on the periodic table so I can figure out its atomic number and figure out what that last orbital that I need to write down is. So beryllium is number 4 on the periodic table. So it's going to have 4 electrons that I'm going to have to put in my orbitals. And it is, if I'm looking at the periodic table, I see hydrogen and helium are the 1s, and it lies in the 2s spot. So it's in the s block, specifically in the second row. So the last orbital I need to write is the 2s orbital. So let's continue. So let me put my orbitals in. So this is going to be the 1s, and this is going to be the 2s. Pretty easy, right? So this is the 1s orbital, and it's spaced away so that I know it's separate from the 2s orbital. Okay? So now I have written out all the orbitals I'm going to need for this specific atom. So beryllium here has 4 electrons I need to put in. So I fill the first orbital all the way, then I fill the second orbital, 2 electrons per orbital, 1 spin up, 1 spin down. So I start always, spin up. So this is the first electron in the 1s. All right? Looks like I'm going to have to go ahead and pair a second electron in there. I don't have anywhere else to go. So 1s, I've got 2 electrons in my 1s orbital. So I've got 2 electrons in their maximum. They're paired up, spin down. I've finished that orbital. I'm going to move on to the next orbital, the 2s orbital. So I'm going to put my electrons in. So I have 3 electrons total in my drawing. I only have 1 in my 2s. However, I need to have 4 electrons in my drawing. So therefore, I'm going to have to pair something up in the 2s orbital there. So I'm going to put a spin down electron there in my orbital. So this is the orbital diagram for beryllium. The orbital diagram for beryllium just is 2 blanks or 2 boxes, arrows, spin up, spin down, 4 electrons per box, or 4 electrons total. So again, this is the orbital diagram of beryllium. So let's go ahead and do the orbital diagram of sulfur as well. So, okay, orbital diagram for sulfur. So if I'm looking at sulfur on my periodic table, it's number 16. So I know it's going to have 16 electrons in my drawing. So if sulfur has 16 electrons, I check out where it's located on the periodic table to see that those 16 electrons, the last orbital I'm going to have is the 3p orbital. It's in the 3rd row. It lies in the p block. The biggest, or the last orbital I'm going to need is the 3p orbital. Okay, so the 3p orbital. So let me go ahead and draw that in. So that means I'm going to have the 1s orbital, the 2s orbital, the 2p orbital, so that's 3 boxes, it's a p orbital. I'd have the 3s orbital, and the 3p orbital is the last one we need. So I'm going to put my boxes there. So there are all my boxes. So let me go ahead and write the names of those orbitals in below. 1s, 2s, 2p, 3s, 3p. Okay, so I've written them this way, top to bottom, lowest energy to highest energy. So my energy goes in this direction, technically, if we want to draw that in, for example. Some places you may see it with S at the bottom climbing upwards, showing that the energy is increasing. However, it's kind of arbitrary. We chose it to mean energy increasing. We could have said energy decreasing. It's just all arbitrary anyways. So I draw it this way. If you want to draw it where 1s is at the bottom and you want to climb upwards, that's fine by me. This is just how I learned how to do it. So that's how I do it. So now that I've drawn out my orbitals, I want to go ahead and put my electrons in my orbitals. So I have 16 electrons to pull in or put in. I start adding electrons in my orbitals from the lowest energy orbital up to the highest energy orbital, and I only pair them up when I have to. If I have to pair them up, they go spin up, spin down. So let's do sulfur. So sulfur here has 16 electrons, so I'm going to start filling them in. So there's 1 in the 1s, 2 in the 2s, or 2 in the 1s. So now I've filled the 1s, 1 spin up, 1 spin down. 2s. So I put 1 in that's spin up. Looks like I'm forced to pair. I now have 2 electrons in my 2s orbital. Let's do the 2p. So remember, if I'm filling a p orbital or a d orbital, I keep them separate until I'm forced to pair them up. Okay? So I would fill this out like this. 1, 2, 3 electrons. However, I still have more electrons to put into my diagram, so I'm going to have to pair them up. So this is 4, 5, and 6. So 6 total electrons can fit in a p orbital. 10 total electrons can fit in a d orbital. So I put 6 electrons there. So I have put 10 electrons into my picture so far. So I've got a lot of electrons into my diagram. However, I still have more to go. I've got 6 more. So 10 electrons down, 6 more to go. So that means I'm going to do the 3s here. So 3s, 1 electron in the 3s, 2 electrons in the 3s, 1 spin up, 1 spin down. Now the 3p, okay? So the 3p here gets, we have 4 electrons left to put into the 3p orbital, 4 electrons. So this means I'll have 1, 2, 3, 4. Okay, so now remember, you have to keep them separate in a p orbital and in a d orbital until you have to pair them, okay? This accounts for certain characteristics and things like that. When you have an O2 molecule, you're left with certain unpaired spin-up electrons, and that's what causes it to be liquid magnetic, liquid oxygen to be magnetic. So it's so important to do this. It literally affects what chemistry you're doing if you do not set this up the proper way, okay? So that's why it's done that way. That's why it's oh so important that it stays done properly this way. It was just like we did with our Lewis diagrams, and it's because we're literally doing the same thing. We're putting in the valence electrons the exact same way in the end. So, rant over. Let's continue on bromine. Okay, so bromine is number 35, so we've got 35 electrons to put into our diagram. And it is in the 4p block. So let me go ahead and set it up so that I have enough squares for the 4p block. So this is going to be 1s, this is going to be 2s, then we're going to have the p block, 2p, and remember that's got 3 orbitals, so it's going to take me putting in 3 boxes. So this is the 3s, this is going to be the 3p, okay, so let me go ahead and label those for you. 1s, 2s, 2p, 3s, 3p. Okay. Now I have to continue on. I have to get all the way up to the 4p. Now remember, it's going to look kind of how you move on your periodic table because we're going to have to talk about the 3d orbital. But remember, the 3d orbital doesn't go right here. That doesn't make sense. It's a higher energy than the 4s is. So I like to draw my diagrams like this. 4s, then I'll put 3d right here. Remember, d has 5 orbitals, so it gets 5 boxes. There's 4 boxes, and there's 5 boxes. All right, so that's the 3d orbital, and this is the 4p orbital. Okay, so that's going to take 3 boxes. It's a p orbital. Let's get them in there. Can't forget 3 boxes for a p orbital. Scooch it over so you can see it a bit better. There it is. All right, let's continue labeling. 4s, 3d, 4p. Remember, it kind of is how you move on the periodic table if you can't remember that 3d goes after the 4s. All right, so now that I have my orbitals drawn out, I need to get up to that 4p orbital. I gotta put my 35 electrons in, so I'm gonna go kind of quickly this time. So watch what I'm doing, and I'll focus in when I get down to that bottom layer, that layer that starts with 4, okay? So I'm gonna go kind of quickly. 1s orbital is gonna get 2 electrons, 1 spin up, 1 spin down. 2s, same deal, 1 spin up, 1 spin down. 2p, 1, 2, 3 spin up, gotta pair them, add the spin down. So I've got 6 electrons in my 2p orbital, 2 per box, 1 spin up, 1 spin down. 3s gets 2, 1 spin up, 1 spin down. 3p gets filled in the same way. 3 spin up, then we add our spin downs because we're forced to pair, okay? So this is taken up, so that's 10, so I've got 18 electrons in my diagram so far, and I need to add the last electrons here. Okay, so I got to add my last little electrons in here. So let's do the 4s. 4s should be pretty easy. Electron number 19 there, spin up. Electron number 20 there, spin down. Okay, 4s. Now I got to fill out the 3d. Remember, d and p, we get all spin up electrons until I have to pair them up. So I do each orbital separately, so I'm not going to do spin up all the d, all the p. Nope. All I'm going to do is I'm going to do just that d orbital, and I'm going to go spin up and spin down within that d orbital and put my 10 electrons in there. So currently my diagram has 30 electrons in it. I need to add 5 more to get up to my 35. So let's add them to our 4p orbital. So that's going to be a spin up, spin up, spin up. That's 3, that's 4, and that's 5. I got to pair the last 2 as spin down in my orbital. So that is how you draw the orbital diagram for bromine. And let me know if you have any questions about orbital diagrams. I've given you some more practice examples on your screen, but we're going to move forward and talk just a bit more about another kind of representation as well. Okay, so we've spent some time talking about orbital diagrams. However, we do have other ways to denote the same information. Orbital diagrams are kind of big and clunky. You gotta draw these big boxes, and it gets in the way. It can be kind of hard to see what's going on. So we have something called the electron configuration. So on your screen over here, you'll see that we have the both the orbital diagram and the electron configuration for the same elements. So you can see the electron configuration is just a quick way to write that out rather than having to draw out this big old picture. So electron configurations are more compact than orbital diagrams are. They make it easier to see what's happening, so they don't take up so much space. However, so it can be way harder to see how far or how many electrons are total are in certain orbitals in an orbital diagram because everything's more spread out. So in a electron configuration, it can be easier to see the total number of electrons in a specific orbital. However, it is harder to know how many unpaired electrons something might have. You have to think a little bit harder about it. Whereas in the orbital diagrams, it's so easy to see what's paired versus unpaired. So kind of depending upon what information you're looking for, you might choose to draw or write one or the other. So electrons configurations use the letters and numbers of the orbitals to denote the same information, but it uses a superscript, aka exponent number, to denote the number of electrons in the orbitals instead. So over here, you'll see that it's written with the principal quantum number first, with the letter second and with the number of electrons in that orbital as the exponent. So lithium has the 1s orbital with 2 electrons in it and the 2s orbital with 1 electron in it. Beryllium, we drew this orbital diagram earlier. It has 2 electrons in the 1s orbital and 2 electrons in the 2s orbital. So on and so forth. You can see here that it kind of, those s orbitals always have 2 in them, and now we're increasing the number of electrons in our p orbital, okay? So we're writing the name of the orbital, and then we're putting that number of electrons as the exponent, okay? So how do we write electron configurations? So in certain cases, you might write the orbital diagram first if you're interested in that. At this level, I would highly recommend writing out the orbital diagram first. Follow all the steps, triple check you followed all the rules, that you have the right orbital diagram. From there, you should write the letter and number of each orbital from lowest energy to highest energy, and as you're doing that, you make sure you write the number of electrons in that orbital as a superscript unless you're told otherwise, okay? So here's the deal. Look at your screen right now. Can you read what this says? I cannot read what this says very easily. If you turn in work that looks like this to me, I will not be able to read it, and you will likely not get very much credit. So please, please, please make sure you're using those superscripts. I probably won't ever ask you to type it into Canvas that way, but if you're handwriting something on a piece of paper, I absolutely have to see that exponent, okay? So let's get some practice here. So let's write the electron configurations of beryllium and bromine first and foremost. So I have put the orbital diagrams there on your screen. So again, beryllium's looks something like this. Okay, so beryllium's orbital diagram looks just a little bit, or it looks like this. So I'm going to try to translate this information into the orbital, or into the electron configuration. So I can see that my 1s orbital that has 2 electrons in it, and my 2s orbital that has 2 electrons in it. So I would write 1s 2, 2s 2. Okay, so this is the electron configuration for beryllium. Let's go ahead and do bromine. So we drew the electron diagram earlier for bromine. So the orbital diagram earlier for bromine. So let's go ahead and write the electron configuration looking at this orbital diagram. So I'm looking at my 1s orbital. My 1s orbital has 2 electrons in it. My 2s orbital has 2 electrons in it. My 2p orbital has 6 electrons in it. 1, 2, 3, 4, 5, 6. My 3s orbital has 2 electrons in it. I'm running out of space. 3s has 2 electrons in it. 3p has 6. 4s2. Jeez. 4s2. 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3d10. Just keep running out of space. 3d10, and then 4p, and now I gotta be more careful. 1, 2, 3, 4, 5. So I would put a 5 here. Okay. So if an s orbital is full, it's going to have a 2. If a p orbital is full, it's going to have a 6. If a d orbital is full, it's going to have a 10. Because a p orbital or an s orbital has 1 orbital that 2 electrons can go into. So if it has 2 electrons, it's full. A p orbital has 3 spots, 3 boxes for electrons to go into, so there can be a maximum of 6 electrons there, okay? And D has 5 boxes, so there's a maximum of 10 electrons. So only the last orbital is going to be the one that's not full. So when I'm looking at this, I could kind of take a shortcut. So with chlorine, let me show you how to take a shortcut. So chlorine here, if I want to write the electron configuration for chlorine, I see that it's number 17 and it's in the 3p block. So it's in the p block and it's in the third row, so I'm going to say its last orbital is the 3p orbital. And if I count how many electrons there would be there, I can start from aluminum and go, I have 1 electron for aluminum, 1 electron for silicon, 1 electron for phosphorus, 1 electron for sulfur, and 1 electron for chlorine. So that means my 3p orbital, in the end, is only going to have 5 electrons in it. So when I'm writing my electron configuration out, I could already just know this to be full up until that p orbital, okay? Full up until that p orbital, and we should have 17 electrons total. So that would be 1s2, 2s2, 2p6, 3s2. So I know everything except for my last orbital is going to be full. And if I count up my total number of electrons here, I have 2, 4, 6, or so 2, 4, 10, sorry, 6 and 4 is 10, and I have 12. So I have 5 electrons left over. So those 5 electrons are going to go in the p orbital. So you could either look and see that chlorine is the 5th in the row in the p block and say, okay, that means it's got 5 electrons in the p orbital. Phosphorus is 3rd, so it would have 3 electrons. Sulfur is 4, so it would have 4 electrons in the p orbital. Or you can say, all right, I know everything except for my last orbital is going to be full. These orbitals have 12 electrons, so I must have 17 minus 12, 5 electrons in that last orbital, okay? So everything is full in orbitals except for that exact last orbital. That's the only one that's going to have something that's unpaired. Except for sometimes in that F and D block. That's why we're not doing it. And that's why we're not doing it, okay? So in our case, this is always going to hold true. So that is how you write electron configurations. So I've given you a couple of examples how to go from that orbital diagram, and I've given you one example here with chlorine about how you might think about it in a quicker way. If you want to draw out the orbital diagram, go for it. Draw out the orbital diagram first. But you could also do the same thing that I showed you here. Assume that every orbital except for the last one is full. Figure out how many electrons are left once you've filled all those orbitals. And then write your last one with just that shorter number of electrons in it, okay? So the electron configuration again for beryllium is 1s2, 2s2. Bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. It's just kind of become a habit over the years to be like 1s2, 2s2, 2p6, 3s2, 3p6, so on and so forth. So it kind of becomes a rhythm and it becomes familiar when you start writing these things out in order. So I've given you some more practice with electron configurations here. So you can go ahead and try to write those out as well. And remember, in an electron configuration as well, we do have that switch where we'll see 3D comes after 4S. So in electron configurations, we're always still writing the orbitals in that increasing energy orbital or energy order. We're just writing them in a line with letters and numbers instead of drawing a picture. So, last chapter, we just kind of skipped along and said valence electrons is the same as the number of the group number on the periodic table. Go. However, we didn't really talk about why this occurs. And this whole concept of the way orbitals are arranged and the way we can think about the way electrons lie in the orbitals, we can kind of figure out which ones and which orbitals hold the valence electrons in the end. So remember, core electrons are close to the nucleus in the center. Valence electrons are that outer shell. They're the ones kind of floating around on the edge that can participate in the chemistry. So now we can actually put a name on them. So valence electrons are all the electrons in the outermost layer. What do I mean by layer? I mean all the electrons with the highest principal quantum number. Even if they are not the highest energy orbital when we write them out, we care about the highest principal quantum number in every shape of orbital with that highest principal quantum number, okay? Core electrons, everything else. Valence electrons are what's on the edge, so core is in the center. It's everything else. So we look for the valence electrons, and then the core is everything else. So if I'm looking at the screen here, I can see that I have silicon, which has the core electrons highlighted in blue and the valence electrons highlighted in yellow. So this means that only the highest energy level here, the highest principal quantum number, those are the valence electrons, which in this case happens to be 3s2 and 3p2. So that means that silicon has 2 valence electrons in the s orbital, 2 valence electrons in the p orbital, so it has 4 valence electrons. So, if I go look at the periodic table, how many valence electrons did we say silicon had before? 4! There we go. We explained it. So that's kind of what's going on here. So it's all of the electrons in the layer with the highest principal quantum number. Those are the valence electrons, which happens to line up the way that it does on the periodic table because of the pure explanatory power of the quantum mechanical model, okay? Now remember what I've said here, that it's the highest principal quantum number, not the highest energy, okay? So that means that when I'm looking at selenium here, the valence electrons are the 4s2 and the 4p4, okay? 4s2, 4p4, not the 3d10, okay? So now, if I had said, now I know that selenium should have 6 valence electrons, 4s2, 4p4, 2 and 4 is 6. That matches what we predicted before on the periodic table. There's been a periodic table on my wall over here the whole time. That's why I'm pointing over there. So selenium, by our way before, was predicted to have 6 valence electrons. This has 6 valence electrons. If I take what's in the highest number of electrons in the principal, the total number of electrons in all of the orbitals with the highest principal quantum number. Now let's say I included, and I just said, okay, the highest energy orbitals. If I included that 3d10, well then I would say that there are 16 valence electrons. But that's not what we're expecting. We're expecting 6 valence electrons. Again, it's only the ones in that highest principal quantum number, not highest energy level, highest principal quantum number. So now instead of just saying a number of valence electrons, I can tell you which orbitals contain those valence electrons. So if I give you an orbital diagram or an electron configuration, you should be able to identify the core electrons and identify the valence electrons. So if I look at what we have written here on the screen, if I'm looking at bromine, I have the orbital diagram here drawn for you. So if you want to look at the orbital diagram, I'm wondering which ones are the valence electrons. Well, this tells me, I'm looking through it, it looks like I've got 1s. Well, I'm already beat out by the 2s, which are beat out by the 3s. I'm looking for the orbitals with the highest principal quantum number. So, okay. I've got 4. It looks like 4 is the highest number I have. So that means I have 2 from the S and 5 from the P. So 2 from the S, 5 from the P. So my valence electrons come from the 4s2, 4p5 orbitals, and there are 7 valence electrons in bromine as we would expect. So again, 4s2 and 4p5, those are the valence electrons, and the core electrons are everything else. Yes, that 3d10 included, even though it's higher in energy than the 4s. We only care about the principal quantum number here, okay? And again, we got 7 valence electrons in the end. 2 and 5 is 7, and that's what we expected, so we can kind of double check ourselves. Okay, what about krypton? Well, I've given you the electron configuration for krypton here. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, right? So now I need to identify which are my valence electrons. So if I'm looking at krypton here, remember, I'm just looking for that highest principal quantum number, which again happens to be 4 in this case, so I want to look at the valence electrons. So that would be 4s2, 4p6, so 4s2, 4p6. That gives me 8 valence electrons. That's what I'd expect. So valence is 4s2, 4p6, and core is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So you can kind of see here that bromine and krypton have the same core. They just have one different valence electron. Okay, kind of cool. So I've given you some practice problems for determining the core versus valence electrons in some other atoms. However, I've not given you the orbital diagram or the electron configuration, so you may need to write those for yourself first. Unless you can get all of the information you need from the periodic table, then you can figure it out on your own. So there's the answers for that. So why does all this stuff matter? Why have I gone on this rant about electrons? So remember that usually only valence electrons are used when an atom participates in a chemical reaction. So what an atom can do is largely determined by its number of valence electrons in the end. So each column on the periodic table has the same number of valence electrons. We discovered this last chapter. So this is why we chose the periodic table to be the way that it is. We didn't realize that's what we were doing. But in the end, all of the chemistry and all of those properties we were lining up are due to those valence electrons and what orbitals they lie in and what chemistry they participate in. So again, doing this and lining these up in this way allows for trends of properties to become apparent when you see the periodic table. So that's why hydrogen is in the first column. That's why it's our exception, is because it's got one s electron and it's got one valence electron. So it sits so well sometimes in that first column. And that's why helium is all the way across on the other side of the periodic table, even though it's an s block element. Really what's happening is that it's got that full valence shell. Remember, it only wants a duet. Its 1s block is full. It's 1s2. It's full. So it behaves more like those full shells of valence electrons. Okay? So that's why it sits over with the noble gases and is a noble gas. So again, doing this allows for trends of properties to become apparent when we look at the periodic table. So this was, again, things like electronegativity, size, how much energy it takes to pull off an electron from that atom called the ionization energy, how metallic something is and how much it behaves like a metal, okay? So information like this contained in the periodic table was what actually allowed scientists to seek out and discover the missing elements. So that's what set off the hunt to get all of these elements named after you. And you worked so hard to find one of those gaps to exploit all of those different trends that we found in the periodic table to be able to find that atom before we knew that it was even all of this going on. So the information that we have learned about modeling atoms with the quantum mechanical theory allows us to predict in a relatively accurate manner what properties and behaviors atoms might have. It's pretty cool. So please let me know if you have any questions. It's kind of a cool topic. This is my area of chemistry. I really love it. When I was in graduate school, what I was studying was solutions to Schrodinger's equation for those F-block elements. So everything in the lanthanides and the actinides. I was working on compounds that contained lanthanides, and I was trying to solve these quantum mechanical models to be able to predict things about the way lanthanides would behave in their chemistry. So I was predicting information about molecules that we don't ever really see exist, that maybe exist for a split second in nuclear waste. I was able to predict things about them. And when I'm able to predict things about them, I could take that information and for nuclear waste, for example, we could apply that to how we might use different properties to separate out different compounds in nuclear waste so we could reuse it or something like that. So wow, the quantum mechanical model of the atom has such explanatory power that what I was using that quantum mechanical model for in graduate school was to give me some information about some molecules. And then we could use that information to separate nuclear waste. I mean, we didn't get that far, let me tell you. We were on the basic trying to nail down our model so that it would show us the properties we were expecting, but the explanatory power of the quantum mechanical model blows my mind every day. So, again, let me know if you have any questions. That's chapter 9.